audible? Can okay, can you please confirm? Am I audible? Yes or no? Yes, okay. So today is the seventh introduction session on design of steel structure. So let's quickly start the session. On the last introduction session, we have started learning about the compression member, right? Where we have specifically learned about the mode of failure of the compression members. Then we have learned how to calculate the design compressive strength. So today first we will revisit the section. First we will uh, learn how to calculate the compressive strength, which factors govern that compressive strength and how to deal with them. Then we will learn how to calculate the compressive strength of the angle strut. There we will learn how to calculate the compressive strength of single angle strut and double angle strut as well. As then we will learn the steps of how we can design a compression member. Then we will go to the built up sections. Okay, so compression member, right? We are learning about the compression members. So first quickly revisit that thing, that what do you mean by say compression member. So a structural member that is straight and subjected to compressive force along its axis, we call them compressive members. So we have come across different kind of compression member, like in building we have steel columns whom we call the sanctum. Then we have strut in a roof truss, and the principal you know compression member in crane जिसे boom बोला जाता है. Then we have went through that this kind of member, the failure criteria for this kind of member. You can imagine that one member which is subjected to compression along its axis. So first thing, if the member is short, then the crushing or quashing will happen, and we can calculate the crushing load as yield strength into cross sectional area. That means we are assuming yielding as the failure mode or failure criteria. Then local buckling can happen. That means individual component of the member can buckle, like this for this channel section, either this flange can buckle or this wave can buckle. And most importantly, for the slender members, we have overall flexural buckling, where the member will buckle about its minor axis. That means, for example, if we consider this rectangular section, it is obvious that moment of area or moment of inertia about this axis, x-axis, and moment of inertia about y axis will be different. That means we will have a minor axis or weaker axis. So about this weaker axis, this column will get buckled. Okay, then we have the torsional buckling. So mainly two mode of failures, or two phenomena of failure occur. First thing is crushing or quashing, and the second thing is that overall flexural buckling. So to calculate that compressive strength, on the previous lecture we have learned that we first we need to calculate, or we need to find out under which buckle class that particular member comes under. So different kind of sections we can use as a you know that compression member, like I sections, channel sections. It can be single sections, and it can be the built up ones. So first, from this table number 10, we need to identify under which which buckle class it comes under. That means we need to find it out the buckling about its both the axes, about x-axis and y-axis, and based on that, you know or based on that, we can find out that imperfection factor. We can find out that FCD value, which we have already discussed, but we will go through that once again. So you know first thing, a compression member or column. Firstly, we are talking about the columns. So obviously we need to have a effective length, we cannot follow that Euler buckling formula, because here there is some imperfections, like on the previous classes I have talked about this, like imperfection regarding the material, regarding the loading conditions, regarding the end conditions, and all of these things. So for this purpose, the effective length of a column can be calculated using the value, or the value of k we can find it out from table 11 of your IS 800. Okay, so, or whom we call the effective length, the length between the point of contact flexures. Now we, from this table we can understand, based on the uh, end condition, we can find it out what should be the effective length. Now one more thing, how to calculate the design compressive strength. So our code clause 7.1.2 gives the idea about how you can calculate the compressive strength. So it's not, it's just like the compressive force. So what will be that? It's the area into the stress. That means my design compressive strength, PD, design compressive strength, should be equals to AC. That means area of the compression member into FCD, that is the design compressive stress. Now this FCD, how we can calculate it? On the previous lecture I have shown you two methods. One, we can directly find it out from the table 9A to D, or A to C, sorry, not D there, or we can use the formula. So first let's see what code says. So clause 7.1.2.1, here the clause give the formula to calculate the value of FCD. How we can calculate the FCD value? The FCD value can be calculated by Fy by gamma m naught divided by phi plus phi square minus lambda square. Now what is that parameters? I will go one by one. Now what is that phi? Phi is a parameter which catered the imperfection factor alpha. Here that alpha is the imperfection factor. Okay, and from where we can find it out, the imperfection factor? We have the table for it. We have, based on the buckling class from table 7, we can find it out the imperfection factor value. Then let's go back to that equation and understand the other parameters. Now phi, to calculate phi we need alpha. How we can calculate alpha? Based on the buckling class, we can find it out alpha from that table. And lambda, what is that lambda value? So lambda is the, we know it's the effective slenderness ratio. And how we can calculate it? We can calculate it using that formula Fy by FCC, where FCC is nothing but Euler buckling stress, and that can be calculated using that formula pi square E by KL by R square. Now using that whole thing, so here we can easily calculate the phi value and we can calculate the lambda value. So if we can calculate the phi and lambda value, we have FCD value. But this clause says our FCD value, that means design stress value, is limited by Fy by gamma m naught. That means it cannot go beyond that value of Fy by gamma m naught, because in compression member we have considered the yielding as the mode of failure. Okay, now that value should be equals to this. Now what is this? Here one thing is there with the value of Fy by gamma m naught, that is chi value, that chi. And what is that chi value means? That caters, this caters for the stress reduction factor. Now how we can calculate this value? This value also can be calculated using this formula, or we have another thing, that we have some tables in our code, that from table 8A to D, based on the buckle class, we can find it out the value of zeta. Okay, based on that Fy, if you have Fy value, say for example Fy you have 250, and lambda value that comes as, say for example 100. So what should be the value of chi here? And this is comes under buckle class A. So this is table 8A. That means that table will give the information about the buckle class A. So here my Fy is 250. So here mark the 250 here. So where is 250? 250. Here 250 joule. Now I need for 100. So here 100 is there. So we have the value of chi directly from here. And also that if you can find out the value of chi, then you can easily calculate the FCD value using this equation that provides here, right? Now one more thing I have told you, that you can directly calculate the FCD value based on the lambda. So how you can calculate it? So you can calculate it from these tables from 9A to D. So for example, you have a I section and you have found out that this comes under buckle class A, and you have lambda is equals to, say for example, 100, and your Fy yield strength value is 250. So first buckle class A, that means you will look for 9A, table number 9A. When you found out the table number 9A, then go and find it out for FCD value. So 250 here and 100 value here. So the FCD value will be this value. Okay. So by this way, we can calculate the FCD value. So let's quickly solve one example so that this concepts will get more clear. So here some limiting values for lambda, like we have discussed on earlier, that if a member is subjected to only dead load and superimposed load, then the value of lambda should be 180. And I will not read it out one by one, so you can take the value of lambda from here. Okay, so so let's quickly solve one example. So like here, what the example says, determine the design axial load on column section ISMB. So we have used an I section as a column where ISMB 400 is used. Okay, no problem. The height of the column is 3.5 meter and the column is pin ended. That means the length of the column is 3.5 meter and it is, both end are hinged. Consider Fe 410 steel, E is equals to 2 into 10 to the power 5, and let's say Fy yield strength is equals to 250 MPa. Okay, so first we have that the column section is made from ISMB 400. So first look for ISMB 400 properties. From where we can get the ISMB properties? From SP6. So here the SP6. So we have ISMB 400. So here ISMB 400 is here, and all the values of ISMB 400 is given here. Like wait, sorry. Then cross sectional area. What should be the height? Then all of these things, and the radius of gyrations about both the axes, you can find it out from here. Now when we have this data about ISMB 400, what will we do? So here I have fetch that data from that table of SP6, where I have taken the H value, the depth, TF, thickness of the flange, thickness of the wave, width of the flange, cross sectional area, and two radius of gyrations about two axes. Okay. So here we can see that one radius of gyration about the principal axis is much more than the radius of gyration about the minor axis. Okay, that is the main problem about single section. So when we use them as a compression member, we will discuss it when we will go into that built up section. Okay, that's why we need that built up sections more properly. So first thing, we have all these data. Now what do we need to do? We need to find it out under which buckle class this I section comes under. So how we can find it out? So for that, what first thing we need to find it out, that what is the value of H by BF. So H, that means the depth of the or height of the I section, that is 400, and the value of the width of the flange, we have taken it out from SP6, that is comes as 2.85, and which is greater than 1.2. And how I can find it out that 1.2? Because our that table of buckle class here look. So for the I section, we need to look here. So first thing, we need to check the first criteria. What that criteria says, if B by BF or H by BF, that means overall depth by thickness of the width of the flange is greater than 1.2 and the thickness um, sorry that uh, thickness of the flange is less than 40 mm, then this I section will comes under buckle class A and B. That means about ZZ axis or about XX axis, it will buckle about A, or it will comes under buckle class A, and about YY axis it will comes under buckle class B. So first thing, let's check the criteria first. So what is the value of B by BF? Because our TF, the thickness of the flange, is less than 40 mm. Okay, so I think that will comes under that buckle class A and B. So TF is less than 40 mm and this is also 1.2. That means it comes under buckle class A. That means it will buckle about XS axis under class A and about YY axis under class B. So if we consider this is XX axis and this is YY axis, that means about that, or this XX axis is here denoted by ZZ. Okay, this XX is nothing but denoted here as ZZ axis. So about this axis, it comes under buckle class A. That means we need to check for that buckle class A about this axis, and about the minor axis or Y axis, we need to check against the buckle class B. So first we will check for buckle class A about its major axis ZZ. So for buckle class A, first thing what we need to find it out, the lambda value. So what is the lambda value? Lambda is nothing but effective length KL by RZ YZ, because we are talking about ZZ axis, right? That's why the radius of gyration about this axis we need to consider. So here both end are hinged end, so 1 into 3.5 meter, I converted into millimeter, divided by RZ. RZ we have taken it out from SP6, which I have already shown you here. The value of R XX value here, you will find out that 16 point something. That is in centimeter and I have converted it into millimeter, so that's why 161.5. So lambda value comes as this. I have the value of yield strength 250. It comes under buckle class A. So go to table 9A and look for what is the FCD value. So we have the table here, the value, the table. So we have 250 is our yield strength value, and the lambda value. The lambda value comes as 21.66. So go and check the values here. 20. So we don't have 20, 21. So we can take the value of 20 or we can do the linear interpolation. So either we can take the value of 20 or we can do the linear interpolation. So first I have shown the linear interpolation value. Okay. So for the value of 120 or 20, the value comes as about buckle class A, it comes as 20. Okay. So for that value, here we have done the for buckle class B. So for buckle class A, the calculation is not here actually. So you can do the calculation from there. You can do the linear interpolation. Like for the buckle class B, I will show you the calculations. Like for buckle class B, we have the value of lambda here. So first thing, you for the linear interpolation, here 124 value is coming. So here obviously the 124 value is not there. 120 and 130 value is there. Okay. So what we will do? Take that value of 120 and take the value of 130 and do the linear interpolation. And how the linear interpolation works, here just write like this. This is your x1 value, this is x value, the unknown value, and this is the x2 value. Corresponding to 120 we have, 130 we have, but we need to calculate the value of 124. So it's a simple formula: x minus x1 divided by y minus y1 is equals to x2 minus x1 divided by y2 minus y1. So by this way you can calculate the value of FCD. So FCD about buckle class A comes if previously if you do the calculation same way, or if we can take the nearest value for the previous calculation. So what that comes as for buckle class A, I think that will comes nearly for 20, that will comes nearly as 0.99. So we can not 0.99, the value is given later here, for 20 to 16, almost 216, and we can take the nearest value, or we can do the interpolation like what I have shown for the buckle class P. So now the point is, what I am trying to say here is, when you have calculated two values like FCD about two axes, about this A, that means about your major axis, and about the minor axis. When you have calculated this, then your FCD value should be minimum of these two. That means, you know, if we consider the maximum value, what will happen? Then ultimately, that minor axis or weaker axis will get buckled after that certain value of FCD. So we need to consider the minimum value of FCD here. So about major axis, and for buckle class A, the value comes as 226, and about buckle class B, here the calculations are there for the buckle class B. For buckle class A, you can directly take 20 value. For 20 it's 226 already there. So now the FCD value, you have the value of FCD. Now you can calculate the design compressive strength as per that clause 7.1.2. So how you can calculate it? So it nothing but it comes as PD is equals to AC. That means the area, whatever for the ISMB 400 we have found it out, and the value of FCD. So that ISMB section, when we have used as a channel section, then this section can carry that amount of compressive load safely. Okay. So by this way, using that table given in 9.1 to 9A to 9C, we can calculate the value of FCD. Now we will go for with the codal formula, right? So first, for the codal formula also, first we need to find it out what the buckle class. So it's the same problem. We have found it out that about its major axis, it comes under buckle class A, and about its minor axis, it comes under buckle class B. Effective length we have calculated earlier. It's a hinge end. That means effective length will be simply the length. Now first, to use the formula FCD equals to Fy by gamma m naught phi plus pi square minus lambda. First, we need to find it out the value, lambda value. Now, here we have two lambdas, about Z and about Y. So first, what we will do? First, we will calculate for about ZZ axis, which comes under the buckle class A. So what will be that? Lambda Z equals to Fy by FCC, where FCC is, Euler buckling stress. FCC is equals to pi square E by KL by RZ. Look, here I have used the RZ. Why? Because now we are calculating, considering the buckling about ZZ axis, and this comes under buckle class A. So that lambda Z value comes out as 0.2439. Now it comes under buckle class A. Go to table 7, you will find out the imperfection factor value. It is 0.21. Now we can calculate the phi value. That phi value comes at 0.534. Now these all calculations are for buckle class A about ZZ axis, the first criteria. But we have seen that I section also comes under that buckle class B about its YY axis. So these all calculations are for this. Now we can calculate the FCD value. FCD, put all these values in equation. Fy by gamma m naught phi value we have calculated as 0.534. That comes, FCD value comes as 225.2. And from the table, what we have calculated the FCD value? That FCD value comes as 226. So almost nearly same the values will come. So here we have found out 225 point something, and there to 26. So almost similar kind of thing. Now what you have to do? You have to do the same procedure for the buckle class B, which buckle under YY axis. So for this, same repeat the same procedure. Alpha for the buckle class B, the value of alpha is 0.34. Then you need to calculate the lambda value. So here to calculate the lambda value, you need to consider the RZ value. RZ, okay? Sorry, RY, because we are considering the buckling about YY axis here. So here you can see that 28.2, that value is the value of RY. So phi value, you can calculate it, and FCD value. So that comes at 87.6. So what is the value of FCD you will consider for this I section? That should be minimum of the FCD about ZZ and FCD about YY. So that comes as 87.06. What should be the compressive force that that I section can carry? That is the area multiplied by the value of the design compressive strength. So by this way, either directly we can use the table of 9A to C, or we can calculate it using the Codal equations, which is given in the form of imperfection factor, stress reduction factor, etc. So this is how we can calculate the design compressive strength of a column. Now we will move to compressive strength of an angle strut. Okay, that means here generally for trusses the angles are used. Equal, it can be equal or unequal. Generally unequal angle sections are used. So angle section can be used as a tension member. We have seen on the classes of design of tension member. Now we will see that angle section here, say this is ISA, say 75 into 60 into 8. That means this leg is 75 mm, this is 60 mm, and the thickness is 8 mm. So here we will see that as a compression member also we will use that single angle as well as double angle section. So first we will learn how to calculate the design strength of a single angle section. Now in angle sections, if the load is concentric, then we will directly calculate this design strength using the same formula whatever we have just went through. But generally what happened, these angle sections are loaded through one leg. That means an eccentricity will produce. So for this thing, the design strength should be calculated using clause 7.5.1.2. And by the way, clause 7.5 will give you the detail about the angle strut. So here the screenshot of the code is there. So I will go into it just little later. So what I am saying, if the load is concentric, then we don't need to worry about calculating the PD value in different way. But if there is eccentricity is there, that means particularly loaded through one leg, and this is the most happening phenomena for the angle strut. So for these cases, one thing will change in calculation of FCD. How we can calculate the FCD value? Using this equation, where the lambda plays a vital role. So here the lambda value, the code says the lambda value should be calculated using that formula, and that formula includes some factor k1, k2, k3, and some parameter of lambda vv and lambda phi. So what is that? We will, so what that k1, k2 and k3 means, they are the factors which which deals with the rigidity or fixity of this member. So here the value of K1, K2, K3 is given in table number 12 of your IS 800, where this depends on the number of bolt and the end condition. Like if we have more than 2 bolts and if the end condition is fixed, then the K1 value should be 0.2, K2 value should be 0.35, and K3 value should be 0.20. Now if we have 1 bolt or the condition is fixed, then subsequently the value will change. And using the table 12, we can find it out the value of K1, K2, K3 based on the number of bolt used there or the fixity condition. Whatever, if this is a fixed case or this is a hint case, whatever it is. And the value of lambda VB, how we can calculate the value of lambda VB? So lambda VB here, all these equations are given on the clause 7.5.1.2, loading through one leg. You can visit this clause and these equations are there. So lambda VB can be calculated using L by RVB. What is that RVB? This is the, here it is written, this is the radius of gyration about minor axis. That means the minimum of radius of gyration about ZZ or YY axis. Okay. Now, what is that sigma here? That sigma is the, the value of 250 divided by Fy to the power half. That means it's, we call the yield strength ratio. Yield strength ratio. What is that? Sigma means yield strength ratio. And pi square E, we know that values. And how we can calculate the lambda phi? Lambda phi can be calculated using B1 plus B2 divided by 2T upon this thing. So why, what is that B1 and B2? This should be 2, B1 and B2. Okay, here it is written B1 and B2. So I have mistakenly written B1 and B1. So please make it correct. B1 plus B2. What is that B1 and B2? B1 and B2 nothing but it's the width of two leg of the angle section. Say this one is B1 and this leg is B2. So if it is the angle section of 75 into 75 into 10, then B1 and B2 should be 75 into 75. Okay. So using this equation, we can calculate lambda equivalent. And when we can calculate the lambda equivalent value, we can calculate the phi value. Phi, how can calculate the phi value? We have the equation. This alpha, the imperfection factor, we can calculate it from table 7 based on the buckle class. Then when we have the phi value, we can calculate the FCD value. What is that FCD? That is the design compressive stress. Now when we have the FCD value, we can calculate the PD, design compressive strength value. That is nothing but FCD into AC. Okay. So let's quickly solve one example of single angle strut. Then this will be more clear. So here example 1 of your single angle strut. What that example says, an ISA Indian standard equal angle section of 150 into 150 into 12 used as a strut has effective length. Okay, effective length is given 3 meter. Calculate the strength when it is connected by, first case bol raha hai, it is connected by one bolt. Now here the number of bolt, that K value, K1, K2 and K3, what just I have said, this value will be influenced by this 1 or 2 bolts. So first case we need to calculate for 1 bolt, then we need to calculate it for 2 bolts, and then welded connection. The 2 bolt and welded connection will be same thing. So first we will look for 1 bolt connection. What we need to calculate? Calculate the strength, design strength. That means we need to calculate PD. That means we need to first find out FCD value, FCD into AC. And for calculating FCD value, we need to calculate lambda equivalent, right? So how we can calculate lambda equivalent? So let's go step by step. First we have a section ISA 150 into 150 into 12. So when we have this section, so let's go to your SP6 and look for the different parameters. So here we have the value. What was the section for our case? The section was 150 150 12, 150 150 12. So here we have 150 150 and 12. Here the value of 12, right? The thickness. So from here we can find out the cross sectional area. We can find out the value of radius of gyrations. Like here the values are provided about different axes. Okay, and the values also provide here. So here from this table we just collected the value of IS 100 into 100 into 8 mm. So here we just need the value of the cross sectional area, the value of radius of gyration about minor axis, because here RVV that says the minimum radius of gyration. So obviously RYY is the minor axis. So that's why we will just take this value. Now angle sections. Angle sections are comes under which buckle class? Angle sections are comes under, what is the table of that buckle class? Let's go and check it out. Angle sections are comes under which buckle class? Yes. So here the angle section. Angle sections are comes as under buckle class C. So we have the buckle class. We have the radius of gyration value. Now we can proceed for calculating lambda e value. So first, what we need? We need to find it out that K1, K2, and K3 value. So here the fixity condition is not provided. The fixity condition is not provided. So let's consider that it's a fixed condition. Okay, fixed condition. So for fixed condition, what is the value of Q1, K2, K3? Where you can find it out? You can find it out from that table what I just said. So here we have only one bolt and we have considered that the fixity condition as fixed at end. So we have Q1 value as 0.75, K2 0.35 and 20. So let's go to that slide here. So these values are here. What is the effective length here? Effective length will be 3 meter because the effective length is given. And what is the yield strength ratio? 250 by Fy. So, and if you make a root, under root of 1 will be 1. So if you put, 1/2 here, so it will be 1. Now you can calculate the lambda VV value. Lambda VV will be L by RVV. What is that RVV? This is the radius of gyration about minimum or minor principal axis, and which is nothing but RYY here. That sigma here is the yield strength ratio. So if you put all these values here, so this is comes as the 1.15. Now you can calculate that lambda phi value. So let's quickly calculate the lambda phi value. What will be the value of lambda phi? So lambda phi we can calculate using this equation, b1 plus b2. This should be 2, b1 plus b2 by 2t. So here we have 150 into 150 into 12 angle section. So b1 will be 150, b2 will be 150, and 2 into t. What is the t? T is the thickness of the angle section. It's here 12 mm. Okay, that yield strength ratio comes as 1, and the rest of the data is here. So lambda phi comes as this. So now you can calculate the lambda equivalent as per this clause. So lambda equivalent should be K1 plus K2 lambda VB square into K3 lambda phi square. Now put all these values here for one bolt and fixed condition. So you find it out that phi value comes as this. Now when you have the phi value, you can calculate the FCD value. FCD will be Fy by gamma m naught, phi plus phi square minus lambda e square. Now put all these values. This Fy 250, gamma m naught. This is the partial factor safety factor. Table 5. Go to table 5. You can find it out all these safety factors. Now phi we have calculated based on the equivalent slenderness ratio. So equivalent slenderness ratio that comes as this, and based on this calculation the value of phi comes as 1.5674. Now the FCD value comes as 91.3. You have FCD value, you know the area, cross sectional area for this section of ISA 150 into 150 into 12. Now you can calculate the PD value, that means design strength or the forces, compressive forces that this section can carry with single bolt and fixed end conditions. So that comes as 316.1 kilonewton. Now let's quickly go to the second case where this is connected by two bolts. So for this case, what will be the different parameter? The different parameter will be K1, K2, K3. So here we have two bolts. We have again assumed the fixed condition, and we have the values like K1 as 0.2, K2 as 0.35 and K3 as 20. So here I have written down the values. Now you can calculate the value of lambda E and phi And based on the value of lambda in phi, you can calculate the value of FCD. FCD, that is the design strength for this member of 2 bolts. Just we have calculated this. That's why I am not doing the calculation right here. So 91.38 kilonewton that comes as, and PD value comes as 410 kilonewton. What we are seeing that if we increase the number of bolts, the load carrying capacity of the members will increase. And for the welded connection, again, for 2 and more than bolts, the effect for the welding will be same. So for welding also, that member can carry a design compressive load of 410.9 kilonewton. So by this way, we can calculate the design compressive strength of single strut. Now on the last class when we were designing that tension member, we have seen that tension member angle section in tension member can be a single angle section or a double angle section, right? So here also that can be the case. So that means we can use that single angle section as a compression member of a roof truss, whom we call the strut, or we can use double angle section as a compression member. We can place this back to back or face to face, or we can say back to back or on the same side of the gusset plate. Here in between them, one gusset should be there. Here one gusset should be there like this, and these are they are connected like this. So if this type of cases arises where double angle sections are used, so for these things, clause 7.5.2 tells the details about these things. Here double angle chart 7.5. So what okay so what should be the case for double angle struts? So for double angle strut, what this clause says that the effective length in plane of n gusset shall be taken as. That means if the double angle sections are placed back to back in opposite side of the gusset of the section, then for this case the effective length should be taken as 0.7 to 0.85 times of the length. Okay, that means if this type of scenarios occur where a double angle strut, discontinuous strut is, we are going to design them, so for this case the effective length should be considered as 0.7 to 0.85 of L. Now if the angle are placed on the same plane like this, here and here also, and joined like this, so for this case what says, the effective length in the plane perpendicular to that of end gusset, that shall be taken as the center of distances. Or here you can see it, that uh, here the effective length in the plane perpendicular to that of the end gusset shall be taken equal to the distance between the center of intersection. That means simply you have to take the length, effective length, as L. So if the channels are placed, angles are placed back to back on opposite side of the gusset, opposite side. So two cases you just need to consider. One, my two angle sections, two ISS are on the opposite side of the gusset, this case, or the second case is my ISA are the same plane of the gusset, same side of the gusset. So if first case occur when they are on the opposite side, for that case you need to consider the effective length as 0.7 to 0.85 times of the length, and if on the same plane is there, then you need to consider the effective length is 1 into 8. So we will solve some problems, then this concepts will get more clear. So here we have an example that says that we have a discontinuous strut of length 4 meter consists of two unequal angle section of 100 into 75 into 8 is connected to a 10 mm thick gusset plate. Okay, by its longer leg. That means 100 leg is your connected leg. Okay. Now determine the strength if this is connected on the opposite side of the gusset plate and same side of the gusset plate. So first case is the one. Here you can see in the diagram that this is your gusset plate and the angles are placed on the opposite side of the gusset plate. Here you can see that 100 leg is the connected leg and 75 leg is the outstanding leg. So first case, before going to that combined section, first let's try to understand for a angle section where my CG lies. So for a angle section, somewhere here you can see this is a snapshot from the SP6. So here you can see that the CG is somewhere here outside the member. That means your XX axis is somewhere here and your YY axis is somewhere here. This is your YY and this is nothing but your x-axis. So that means we have different radius of gyrations for this member. When we connect this member as a like this, so for this member my x dash will pass from here and my y dash will pass from here. Yes. So for single angle sections, we have the data like we have the radius of gyration value, we have the Cx value, we have the Ix value. But for this arrangement, when we place them on back to back, we don't have the inertia values. So first we need to calculate the area, inertia and radius of gyration for this arrangement. So what will be the area for this arrangement where two angle sections are there? So first, when we will solve this problem, first go to SP6, take all this property like what will be the cross sectional area of IS 100 into 75 into 8, what should be the Rx and Ry value, that means radius of gyration about X and Y axis. I have just shown you how we can find it out these values from SP6. Now Cx values and Ix values. Now for this arrangement, we are talking about the arrangement of two angle section placed back to back or opposite side of the gusset plate. So here what should be the area? So we have simply two angle sections, so just multiply it with 2. So the area of this overall arrangement is 2672 square. Now I'm not considering the area of the gusset plate because for calculating the strength, the gusset plate, the packing plate, the filler plate, this area and strength are not considered generally. So now Rx, what will be the XX value? So here look at this, XX axis is same as my individual XX axis, right? There will be no change in this axis. So obviously there will be no change in radius of gyration about this axis. What I mean to say is for a single angle section, here your XX axis is lies. Obviously when you place this angle section here, the axis about this will remain same. Okay, but the YY axis will change because for the individual members you have YY axis here and you have YY axis here. You need to shift the YY axis from here to here, right? So how we can shift that axis? So we have the parallel axis theorem. So here using that parallel axis theorem, IYY, that means I need to shift my YY axis from here to here. So IYY into a area multiplied by the distance from here to here, the distance. So what will be the distance? We know the value of Cyy or Cxx, the distance like this. We just need to add the half distance of the gusset plate. So Cyy plus Tg. What is the Tg? Thickness of the gusset plate divided by 2. So by this way, we can calculate the y dash of the composite member. that comes as this. So when we have that I y dash value, we can calculate the radius of gyration about this axis under root of I y dash by a dash. So that comes as 32.8. So what should be the minimum radius of gyration? The minimum radius of gyration will be that 31.4 mm. Okay, someone says that my screen is not visible. It is visible, I mean, can you confirm? Okay, so what we have just did, we just shift the axes for this composite section, and we have found out the minimum radius of gyration. Now when we have the minimum radius of gyration, what we will do, we nothing but calculate the effective length. So it's uh, the angles are on opposite side of this gusset plate. So this is your gusset plate and angles are placed on the opposite side here and here. So for this case, we have the effective length as 0.85 L. So that comes as 3.4 meter. What will be the slenderness ratio? Lambda should be equals to LE by R minimum. So R minimum comes as 31.4. So this comes as 108 mm. Now angle sections that comes under buckle class C. So go to table 9C and look for the value of FCD with corresponding to lambda 108 and FY 250. So if you go to that table 9C, so I just shown you how to calculate this. So here the value of lambda is given here and corresponding to 250. So we have 250 value. So 250 go to 250 and we have lambda like for this example, we have two lambda values here like 108. So we don't have the value 108. We just need to do the linear interpolation between 100 and 110. So take the value of 100 here and 110 from here and do the linear interpolation. So if you do the linear interpolation, then you can calculate the value of FCD. So FCD value comes as this. So what will be the design strength or the load carrying capacity? That will be nothing but the strength multiplied by the area. So here 10 to the power minus 3 to convert Newton to kilonewton. So that comes as 258.6 kilonewton. That means when the two angle sections are placed opposite to the gusset and we made a double angle strut, then this member can carry a compressive force of 258.46 kilonewton. Now, if we place them on the same side, what will happen? So here, the second case, we have placed them on the same side. So on the same side, when we place on the same side, what will happen? This axis and this axis will be the axes of the composite section, y dash and y dash. So here we can see that y dash and y dash will be same as a individual member. Like if you see this diagram, what I have explained just right now here, if you see closely this diagram, then you can understand that why that y and x's axis and which condition we need to transfer these axes or we need to shift these axes. So here you can see that x axis will, for this case x axis we need to transfer, but y that will be same as my composite member for that kind of arrangement. So here we have on the same side arrangement, so we just need to transform that xx here to here. How we can do it? So here just we can do it 2 into ix plus a into cx. What is the value of cx? Cx is nothing but this value. So here the gusset plate is not there, that's why I didn't add that tg by 2 value. So I x that means the moment of inertia of the whole member about x-axis will comes as this. So radius of gyration about this axis come will that, and y, if this y axis will be same as my single angle section. So see, for the single angle sections that ry dash was 21.8 mm, so that will be same. So minimum of these two, that means 21.8 will be my targeted ry dash value. So if we use this and if we calculate the FCD value from table number 9C, that we can see that the FCD value comes as 116 kilonewton. But for when we have use that on the opposite side, that value comes as more than 240 kilonewton, right? So the point is, when we use two angle sections as a strut, on the opposite side, the load carrying capacity or strength carrying capacity of the strut will be more. So by this way, we can calculate the strength of a double angle strut when they are placed opposite and back to back on the gusset plate. Okay. So till now, what we have learned? So we have learned to calculate the design compressive strength of a column, design compressive strength of a single angle strut, as well as design compressive strength of a double angle strut. Now the thing is how we can, design this compression member. So, during this calculation and of that compressive strength, we have learned that we need to calculate that FCD value. Then we need to calculate the PD value, and here most important parameter is lambda. So how we can actually design a compression member when we only have the load? So first, either you can directly um, follow these steps. Like first, what do we need to calculate? We need to calculate the effective length. And how we can calculate the effective length? We can calculate the effective length based on the end conditions, right? Like we have hinge to hinge condition, or we have fixed to fixed condition, whatever the end condition is. Now, while calculating that FCD value, what we have seen, based on some lambda value, we need to calculate the FCD value, because table 9C, if we go closely the table 9C, we can see that the FCD value depend on Fy and lambda value. So first, initially we don't have any lambda, so we need to consider the lambda value between 30 to 60, or we can consider the FCD value, directly FCD value. The both way you can consider. Now when you have the FCD value, you can calculate the required area. When you have the required area, then go to SP6 and look for a section whose cross-sectional area is more than that required area. Then select that section, and for the section you just calculate the R minimum value. Now with that section and with that R minimum and lambda value, you calculate the PD value. Now check your PD value is more than the applied load or less than. If more than, then it's okay. If less than, then you need to go to again step 1, and you need to check, not step 1, you need to go to step 3, and you have to select a member with more cross-sectional area. So here the step will be more clear when we will design one section, and more specifically we will design a built up section step by step, where you can understand these steps. Like first, what do you need to understand? Like when you need to design one compression member, what values will be given? First thing, that P value, factored load, is given. The end conditions will be given, or maybe the section should be given, but these two things, mostly these two things will be given. First thing, the factored load which we need to transfer, and the end condition. So first, what should be the step? First, you need to calculate the effective length of that member based on the end condition. Now you have effective length, you have L. Now what I said, either you have to assume the value of lambda, or you have to assume the value of FCD. Like FCD for direct compression and tension 0.6 into Fy, like that you can assume the values. Now when you have the FCD values, you can calculate the required area. Now when you have the area and you know which kind of section you need to provide, like you need to provide I section. So go to SP6 and look for I section, and then find it out the I section whose cross sectional area is more than the required area. Now we are talking about the design of single sections as a compression member. Now when you have selected that, let's say we need to provide that I section like ISMB 400. Now from the SP6, just pull out all the data regarding ISMB 400. Now calculate that FCD value again for this member and calculate PD value. Now check your PD value is more than your factored load or not. If more than, your design is okay. If less, then go to step 3 and again select another section of higher cross sectional area. Again calculate the value of PD and fix it out. So this is the process. Now this is for here some value of lambda while designing or while selecting the trial section you can consider, and these are recommended by NPTEL your course instructor. So you can take these values from here to design one compression member. Initially for selecting the section of compression member you can take these values out. Now the most important part is the built up section. So here till now what we have seen that we can use different sections as compression member. We have learned how to calculate the design strength of a compression member as a single section. Now, and we have seen some problems regarding the use of single members. So first, let's have some flavor about the built-up member. Now we will learn built-up member. Built-up member. What do we mean by say built-up member? Built-up member means in that member we have more than one section. A built-up compression member is one that consists of two or more than two rolled sections together. Okay, and they will act as a single unit. And how they will act as a single unit? We have some connections like lacing connections and batten connections. So you have seen this kind of built-up member like in railway stations, in different kind of industrial sets. You have seen the built-up section. So built-up section means in that section we have more than two rolled section and we have tied them together to act as a single unit. Now why we made this or why we need this kind of built up sections, or what is the necessity of this? So let's first go to it, then we will discuss again about the built up section. So if say for example we have a channel section and we have single channel section as a compression member. So we have seen that it's about that ZZ axis or XX axis, the moment of inertia is more. That means IXX is very much higher than your IYY. That means radius of gyration about this axis is much more than this. We have seen, right? One is 100 more than 100 and one is like 20 to 30 like this. So if we use this single channel section, what is the chance there? There is a chance that will buckle under this minor axis. That means about this YY axis, the load carrying capacity, whatever will be the load carrying capacity, we have to go with that load carrying capacity. We cannot go beyond the load carrying capacity. Now the case is if we need to transfer more load, that means about ZZ axis it can transfer more load, but it has one problem that it has one weaker axis and the weaker axis radius of gyration is less. So what we can do, if we arrange these two channel like this, or we can arrange in different manner. The point is if we arrange them in a such a way that our IZZ will equal to IYY. That means we are making two moment of inertia same. That means R, that radius of gyration about ZZ will be equals to radius of gyration about YY. That means we are eliminating the weaker axis. That means we can transfer more loads through that kind of member. So main purpose is to increase the radius of gyration, to increase the cross sectional. One more thing here, for using that one section we have limited cross sectional area, and we have seen that our design compressive strength PD is directly proportional to your cross sectional area required. Yes or no? So two things we have came across, that if instead of one member, if we can make a composite member or compound member using more than two or more than two individual members, then the radius of gyration problem and the cross-sectional required cross-sectional area problem will be resolved. Okay. So now you can understand that why this kind of sections are provided. Like here, two channel sections are placed toe to toe and they are connected using lacing. Here you can see the two channel sections are placed back to back and they are connected with lacing. Here you can see two channel sections are provided back to back and connected with batten. So lacing, batten, this connection system, and here you can see that four angle sections are used and they are connected using lacing systems. So we will discuss in detail on the next class how we can design that lacing batten system, how these lacing and batten systems are affected by different kind of parameters and all these things. So first, now we have an idea that what is a built up section and why we need them. Why we need them? First, to counteract that radius of gyration problem and area of cross section problem. So we have some um, you know reason to go with the built-up section. Like built-up sections provide large cross-sectional area. The cross-sectional area, how much cross-sectional area I need, uh, that can be easily managed by the built-up section. Now, built-up sections, what we have seen that in the built-up sections, the main motto is to make that IZZ is equals to IYY. That means about two axes, the moment of inertia, we will make them same, or radius of gyration, say RZZ, we make RYY equals. That means there is less chance of having one weaker axis. That means we can safely transfer much loads. Here, larger radius of gyration, and one more thing, that different kind of shapes can be achieved through this kind of connections, and which will be very useful for steel structures. So we have now idea that what is a built up member and why we need them. Why we need them? To eliminate the problem regarding radius of gyration and cross sectional area. Now, so what I said, different kind of shapes can be there. Say channel back to back, this is box type, this is channel face to face, and all these things. Okay. So first thing, to calculate the design strength of this kind of member, we need to understand under which buckle class they comes. So they comes under buckle class C. Your table 10 of IS 800 2007 says that all the built up members comes under the buckle class C. Okay. So we have the buckle class. Now we have the value of alpha. We can calculate the value of alpha. We know which table should we use for the calculation of FCD value. So we will use table 9C. Why? Because all the built up members comes under that buckle class C. Now, how to design them? What should be the first step? The first step should be find out the effective length from the actual length and end condition. L. Find it out. Now you need to consider a lambda. Based on that considered lambda, you need to calculate the value of required area. Now you need to provide this required area. Say we have required area, say 2000 mm square. So, and we need to provide two channel section. So we will go to SP6. We will look for one channel section and we will figure it out using two sections what should be the required area. And we will consider two channel sections whose cross-sectional area should be more than our required area. Then what will we do? We will place these members so that our IZZ will become IYY. Now, with that arrangement, we have select the sections, we have placed the sections. Now, for this arrangement, we need to calculate the PD value. Now, if that PD value is more than the design or applied load, then it's okay. Otherwise, you go to directly step 2 or step 3. In step 2, what will you do? You will change the value of lambda. In step 3, if you go to step 3, you will change the value of A. That means whatever the required area, you just need to select more area, more cross-sectional areas, because your load carrying capacity PD is directly proportional to your AC. That's why for designing purpose, always try to choose or pick some sections with with larger cross-sectional area. So let's quickly solve one example so that our these steps will get clear. So here I have provided one example of the built-up member. On the next class we will go in detail of it, but today up to how we can select this member, how we can place them, these things today we will learn, because this will required for your assignments. I've seen that one problem is coming from that spacing, how to calculate the spacing. So let's quickly go through this problem, then we will solve the previous year assignments. So here what that example says, design a built up column 10-meter long to carry a factored load of 1080 kilonewton. The column is restrained in position but not in direction in both ends. That means hinge column. Provide 4.6 grade bolts. Okay. Fe for Fe 410 420 नहीं होगा 410 Fe 410 plates, and design the column. Now here the part, design the column with two channel sections back to back with single lacing system. So lacing system, today we will not talk about the lacing system here, focus on this thing. Two channel sections, so we need to consider two channel sections for this built-up member, and we need to place back to back. This is the back to back position, and if we place them like this is the face to face or toe to toe position. So we will discuss in detail when we will place back to back and when we will place toe to toe, what will happen and what the parameter that will influence by this positioning. Okay, so first step, what should be the first step? Calculate the effective length. So here the end condition is hinge, so obviously effective length will be 1 into L. Or if there are any other end condition, go to table number 10, look for the end condition, and subsequently you choose the value of K for this particular end condition case. Now we have the value of K. Now we need to calculate the value of required area, right? So we have the factored load which need to be transferred. Here the factored load is 1080 kilonewton, so I made it 1080 newton. Now here I consider the value of FCD. Instead of considering lambda, I have considered the value of FCD as 150. Directly I have considered 150, or you can consider first lambda, then from table 9C you can calculate the FCD value. So it's like first primary sizing of or selecting or picking of the channel section. So if you consider the FCD value more than 150 MPa, then I think most of the built-up member will be safe. Okay, so what will be the required area here? A will be 7200 mm square. Now we have that we need to provide 7200 mm square using two channels. So we will go to SP6 and look for which channel section, single section, which we can multiply by into 2, that will be more than 7200 mm square. So if we look that SP6 portion, we can see that ISMC 300, ISMC Indian Standard Medium Wide Channel section of 300 is meeting our requirement. So here if we provide two ISMCs, the area will be 4 5 in for single ISMC the area is 4564, and for two ISMCs if we multiplied it 2 into 4564, that comes as 8 2 2. So it's more than the area required. So our area required something 7200 mm square. So this is more than this. So that was the primary thing what we need to consider while selecting that section. So we have selected ISMC and the subsequent values, like what will be the RYY for ISMC 400, what will be the RZZ for ISMC 400, what will be the CYY value, and what will be the G value, what will be the I value with respect to Z axis, and what will be the I value with respect to Y axis. So all these values we have collected from SP6. Now what should be the second step here? You can see that ISMC, what we have selected for ISMC, we have selected ISMC 300. Here ISMC 300 is here. All the values of ISMC is given. So from here you can pick your ISMC from here. If someone wants to pick ISMC 350, yes, he or she can pick this and do the design accordingly. Okay, you just need to show that the member is safe primarily. Then you need to go for economical sections. That is the next, for the next iteration, for the next steps. Okay, now the next step should be the calculation of design compressive strength of that ISMC 300. So for ISMC 300, we need to calculate the lambda value about ZZ axis. So LE by RZZ comes as this. So we can calculate the PD value. PD will be AC into FCD. FCD value, how we can calculate the FCD value? So lambda value comes as this lambda. Now go to table 9C. Here this is all these things written. So if you go to table 9C, corresponding to value of lambda is equals to 121. This is the value of corresponding to value of lambda 121. You can calculate the value of FCD. So FCD comes as that value corresponding to lambda, this lambda, the FCD value comes as 121 MPa. Now what will be the value of PD here? PD will be AC, the cross sectional area of two ISMCs multiplied by FCD. Then it comes as 1104 kilonewton, which is more than 1080 kilonewton. That's why I am saying that, look, this is very close to your the value or the load you need to transfer. Okay, so whatever we have selected ISMC 300, this is safe with respect to the cross sectional area and load transfer capacity, load transferring capacity. So I am repeating once again. So after selecting the section, what we need to find it out here is the value of design strength of this particular member, whatever we have selected. So we have selected ISMC 300. So for ISMC 300, we need to first calculate the lambda value. So lambda value comes as 84.46. Now corresponding to 84.46. Here, one more thing is here, as the member is lacing member. So for the lacing and battens, we have the some effective length criteria. For now, you just keep in mind that for lacing column, the effective length should be increased by 5%. The slenderness ratio for this lacing column should be increased by 5%, and for the batten column also that will change. So till now, or for now, I am just try to convey the steps how we can go through that steps. So here for lacing thing we need to increase the lambda value by 5%. This is written in your clause there. So when you can calculate the lambda value, now corresponding FCD value you can find it out from table number 9C. And from table number 9C, when you can calculate the FCD value, you can calculate the PD value and check your PD value is more than or less than your PU, factor load value. So here we have seen that factor load value is more than that. Now here that 5% increase in slenderness ratio, that thing I will cover in on the next class. For the lacing, for the batten, we have much more specification regarding that. So that will take time, and regarding this week assignments, you don't need that information. Okay, now what do we need to do? We have two ISMCs, ISMC 300. Now we need to place them back to back in such a way that I yy dash should be equals to I z z dash. So the position of the column or the channel sections are given, that you need to place them back to back. So back to back. So I have placed them back to back with spacing s. My main aim is to make I y dot. That means the total moment of inertia about y of this whole section is equals to I z z. So for a single section, I z z will pass from here. Obviously, from that uh, compound member, the z z axis will remain same. But for the individual member, y axis is somewhere here. That means we need to transfer this y axis from here to here with the condition that my I y dash is equals to I z z dash. So what will you do? Just for I z z dash, this will be 2 into nothing but I z z for individual members will be equals to, now we need to transfer this axis from here to here. So what will be that? So 2, we have two channel sections on two sides. So 2 into I y. That means the y for the individual channel sections plus now a into r square. What parallel laws of parallelogram says? That parallel axis theorem says a into r square. So what will be the value of r? The value of r or h should be this value, h or r. So what should be that? That should be cyy plus the spacing by 2 value here. So a into cyy plus s by 2 third square. Now if you solve this equation, you will find the value of s. What should be the spacing? Spacing means it's the length between, when we place them back to back, it's back of one channel to back of another channel. Now if you solve this equation, you have, or you will find it out, the value of that spacing comes as 183.10 mm. So the main goal for the that, or the main aim for this um, built up member is to make these two moment of inertia equal. So we need to place them in such a way that these two moment of inertia will be equal. So here the spacing s will play a vital role. So we have seen that how to calculate the value of s. Now the next step should be the design of lacing and batten system, which we will cover on the next class in detail. So that's all for now. Now we will solve that previous year assignments and we will close the session. So let's quickly solve the previous year assignment. So till now, do you have any doubt or confusion? You can tell me. Okay. So let's solve previous year assignments. Okay. So first question. What the question? First question says a column having effective length 2 meter. Okay. Effective length is given with both and fixed. So effective length is given. So we don't need the end condition. Now this column is made up ISMB 400. Okay. And the value of ISMB 400, the parameter of ISMB 400, like the radius of gyration about YY axis is given 28.2 mm. And the modulus of elasticity is given. Now, calculate the value of lambda. Lambda. So, how we can calculate the value of lambda? So, we have our clause 7.1.2.1. From there, we see that the value of lambda can be calculated using that equation. Lambda is equals to Fy by FCC under root of Fy by FCC. Now, what is that FCC? FCC is nothing but the Euler buckling stress. So, Euler buckling stress, how we can calculate this? Pi square E by L effective divided by R minimum square. So, The Euler buckling stress FCC comes as 392.43 MPa. Now, if you put this in lambda equation, lambda is equals to Fy by FCC. That means under root of 250 divided by the FCC value comes as 392.43, and this is equals to 0.79. So, option C is the right answer. Okay. Now, move to next question. Now, using the data and result of question number 1, calculate the value of design compressive strength FCD about YY axis. Okay, because the question number 1 is all about YY axis, because the YY axis is the minor axis. So here we have found out the value of lambda from this question. Now here the imperfection factor is given as 0.34. So what do we need to calculate? We need to calculate the value of FCD. So to calculate the FCD value, we need to calculate the value of phi. Because we have the value of lambda, just we need to calculate the value of phi. So phi we can calculate. Phi is equals to 0.5 bracket 1 plus alpha, that is the imperfection factor, lambda minus 0.2. Lambda we have calculated on the previous example, and this. So if we put all this equation, the value of phi comes as 0.91. Now phi value, we have the phi value put in this FCD equation. So FCD will be equals to Fy by gamma m naught divided by phi square minus lambda square to the power half. And from this equation you can see that your FCD value is bounded by Fy by gamma m naught. So your FCD value comes as 166.9 km. So option C is the right answer. Okay. So this equation, all of the value is provided. Now put all these values in this equation, so you can find it out the value of FCD. Now let's move to the next question. Now build-up sections. Build-up sections ultimately leads to an economical design, right? Provides larger cross-sectional area, yes. Provides sufficiently larger radius of gyration, yes. We have just explained all of this. That means all of this will be the right answer. Now, question number 4. So what question number 4 says? That we have an Indian standard angle section of 130 into 130 into 10, having radius of gyration about minor axis. That means R minimum is provided 25.4 mm. Is used as a strut and has effective length. Also effective length is provided. Calculate the value of lambda VV and lambda phi, which are used to calculate the equivalent slenderness ratio. The data is given like Fe410 grade of steel and E value is provided. So to calculate lambda VV and lambda phi, first we need to calculate the yield strength ratio. So here in clause 7.5.1.2, all the equations are provided. That lambda equivalent is calculated using this equation, and lambda VV and lambda phi we can calculate by this. So first let's calculate the yield strength ratio. What is the yield strength ratio? Under root of 250 by Fy. So that comes as 1. Now put in this lambda VV equation. So lambda VV is equals to L. What is the effective length? The effective length is given 2.8. Make it into mm. So 10 cube divided by 1, that is the yield strength ratio. Now under root of pi square into E value you know, 2 into 10 to the power 5 divided by 250. And if you calculate this, that comes as this. Now how you can calculate the lambda phi value? So lambda phi is equals to B1 plus B2 into divided by T by 2 upon that yield strength ratio under root of pi square E by 250. So here B1, we have ISA 130 into 130 into 10. So B1 will be 130 plus 130 divided by, what is the thickness? 10 mm. So T by 2. So 10 by 2, sorry, 2T divided by 2T, divided by 2T. I've written it wrongly. Divided by 2T. Yes. So 2 into T. Now upon that value 1, and if you plug all these values here, so that comes as 0.146. So which one is correct? You just look for it. 1.24, 1.24, and this. So B option will be the correct answer. Now move to next question. Now question number 5 says, using the results of question number 4, find out the value of equivalent slenderness ratio if the connection is made with 1 bolt at each end and consider the fixed condition. So now you need to consider the lambda equivalent value. So lambda equivalent value, how we can calculate the lambda equivalent value? Lambda equivalent is equals to K1 plus K2 into lambda VV square. Lambda VV we have calculated on question number 4 plus K3 into lambda phi square. And lambda phi value we have already calculated on the previous question. So we just need to find it out the value of K1, K2 and K3 based on we have 1 bolt and fixed condition. So table number 12 will give us all this information. So here we have 1 bolt and fixed condition. So K1 will be 0.75, K2 will be 0.35 and K3 will be 20. So here I have written these values. Now lambda VV and lambda phi on the previous we have already calculated, that comes as lambda VB comes as 1.24 and lambda phi comes as 0.146. So if you calculate and solve for lambda equivalent, that comes as 1.31. So 1.31 will be the right answer. Now let's move to next question. When double channel section are selected to build a compression member, what should be the range of slenderness ratio? So I have shown you that table which is provided in your class notes. So there it said that when we have used them, then the range should be 40 to 80. So I will show that table once again. Here you can see double channel sections when we have 40 to 80. So for the other combination also you can find it out the value of slenderness ratio for selecting the members. This is the for primary selections. Okay. Now let's see what the next question says. So here 40 to 60 will be the correct answer. Now a built up section, in built up section member are arranged in such a way कैसे हम लोग arrange करते हैं? In such a way that our I z dot will equals to I y dot y dot. That means moment of inertia along the both axes we make them equal. So our main goal is to make both moment of inertia equal. So the first will be the right answer. Now question number 8. What question number 8 says? A column having actual length 3.5 meter. Okay, actual length 3.5 meter, both end fixed, is made up of ISMB 300. So we have column section of actual length 3.5 meter with fixed end, and we have ISMC 300 as our channel section. Now find out which buckle curve we will use to calculate the design compressive strength. Okay, so we need to find it out under which buckle class that comes under. That means we have to go for that table of uh, the buckle class. So where is that table? Here, the table of the buckle class. Now, what the question says, if only one channel section is there, then it will comes under buckle class C. So here the question says, we have a column having length ISMB. Okay. So we have I section, not channel section. So for I sections, what we need to do? For I sections, we need to check these criteria, right? So check the criteria for the ISMB, not C. ISMB 300 is given. I have, wrongly read these things. ISMB, I section is given. And for the I section, the thickness of flange is given, which is less than 40 mm. So you just need to calculate the value of H by BF. So what is the value of H here? H is ISMB 350. So 350 divided by what is the value of width of the flange? BF is provided here 140 mm, and the thickness of flange is 14.2 mm, which is also provided here, which is less than 40 mm. So, and question says about YY axis. So about YY axis, that comes under buckle class B, and from where we can see it here. So for the I section, these conditions are satisfied, and when these conditions are satisfied, so about YY axis, it comes under buckle class B. Okay. Now if that question is asked about ZZ axis, that ISMB 350 will comes under, that will comes under buckle class A. Okay. Now moves to next question. A column to be designed which should be capable of carrying a design load of 300 kilonewton. Okay. Design load of 300 kilonewton. Now calculate the effective sectional area required to fulfill the criteria and then suggest a suitable section from the options given below. Okay. So first, what is given here? Your PD value is given here, 300 kilonewton. So just calculate A required PD by FCD. Now FCD value is given 150. So that PD value is 300. That means 300 into 10 cube. I make it in Newton divided by the FCD value is given as 150, and if you calculate, then comes as 200 mm square. Obviously, we need to provide a section more than this area. So now look for the options. First option says sectional area of 1460. That means it is less than your 2000. So this is not the option. Now the sectional area is 1660. That is also not the case. Sectional area is 1900. Again, this is not the case. Now sectional area is 2500. Yes, we can go with this section. So this will be our right answer. Now move to last question. I think this is possibly the last question. So here what says a discontinuous strut. So we just have solved this problem. Now we will again solve it. No problem. A discontinuous strut of length 2.5 meter consists of two unequal angle section. Okay, here we have 80 50 into 8 connected to a 10 mm thick gusset. The thickness of gusset is also provided, and they said the longer leg of the angle is connected with the gusset, whereas here says the double angle strut, the effective length you should consider 0.85 L. Assume this, and for ISA the values are given. So here we don't need to think about the effective length. So effective length is provided, and one more thing is provided, that these are connected on the opposite side of the strut. Okay. So first, what do we need to find it out? For single angle section, these values are provided. That means for single ISA, 80 into 50 into 8. For this, these values are provided. But our arrangement is made up with two ISS. So for these two ISS, what will be the total area, it will be nothing but multiplied by 2. So for a single ISA, the cross sectional area is 978. So for two sections, the cross sectional area will be simply 2 into 978. That comes as 1965 mm square. Now here, from here, the x-axis will pass x dash, or we can say the z dash for this section. So for a single angle, the x dash x and for this uh for these two angle sections where we have connected on the opposite side of the gusset, the x axis will be remain same. So the radius of gyration will remain same. So for this axis, x dash and x dash, we need to, so we don't need to shift any axes from, or using that parallel axis theorem. Now for this compound member, the y or y dash axis should pass from this y dash and y dash. But for the individual member, the y axis will, be somewhere here. So we need to transfer this y axis from here to here. So we will use the same equation, I y dash is equals to 2y2, because two angle section is there, I y. This is the moment of inertia about y axis of individual angle section A. That is the, what was the formula of that parallel axis theorem, that I y dash is equals to I y plus A into h square. H is the distance, or distance by which you want to shift the axis. So here is the distance. What should be the distance? So from the single angle section, you can see this small distance from the y axis, to the end of the plate, from the y axis to the end of the plate. This distance is CYY. Now here we know the CYY value up to the end. Then we just need to go up to the middle of the gusset plate. We have 10 mm thick gusset plate, so Tg by 2, we will go up to Tg by 2. Here for calculating the cross sectional area, we will not consider the gusset, as we know that the gusset filler and packing plates will not counteract or contribute anything towards calculating the load calculation. We don't consider this. So if we put this all equation, so we will find out that our I y dashed or y dashed of the, that, two with that two angle sections on the opposite side of the gusset comes as 96.22 into 10 to the power 4. Now you can calculate the radius of gyration about this axis. So what will be the radius of gyration about this axis? Will be under root of that moment of inertia divided by area. So that comes as 22.18. So what is the minimum value? X, about x-axis, that was 25.2. About y-axis, that comes as 22.18. So the minimum radius of gyration is 22.18. Now radius of gyration, we have found it out. We need to calculate the value of the design strength, right? What was the question? We need to calculate the, yeah, we need to calculate the design strength. So let example, we need to calculate the design strength. So up to here we have calculated the value of minimum radius of gyration. Now effective length, we have the value of effective length already provided in the question, that you need to consider 0.85 into L. So that comes as this. So what is the value of slenderness ratio? Lambda is equals to L effective by R minimum. So R minimum, we have just found it out, that R minimum is equals to 22.18, which is nothing but the R about y axis of the uh, compound member. Okay, now we have the value of lambda is equals to 95.81. We have the value of Fy is equals to 250 MPa. Now we have the buckle class C. Go to table 9C and look for the value of FCD. So for lambda 95, there is no value is there. So we need to do the linear interpolation. So for the linear interpolation, simply the linear interpolation is done between the value of I think 190. So this value comes as this, and now you have the FCD value is equals to, like, FCD will equals to 112.87 MPa. Like, this interpolation I have already shown you on the previous examples when we have solved that design strength problem, single angle problem, and all these problems. So you can go back to the video and you can see. So here the FCD value comes as this. Now we can calculate the value of the design strength. PD is equals to AC or AE multiplied by FCD, and that comes as 221 kilonewton. So the question was calculate the design compressive strength. So calculate the PD value. So what was the PD value? Our PD value comes as 221 kilonewton. So this is 221 kilonewton. So that's all for today's class. If you have any doubt, you can ask me. So is it clear? Aman, is it clear? Or you have any doubt left? I think now you can solve all the assignments regarding this. What is the score? Okay, so if you have any doubt, if you don't have any doubt, then we can end the session here. We will meet on the next Monday. Thank you. Good night.